our thumbnails, we are talking about three basic principles for assigning electron across the various orbitals. And when we mention basic principle for assigning electrons, we are referring to Pauli's exclusion principle. We're also talking about Hund's rule of maximum multiplicity, and then we're talking about Aufbau principle. And that is what we're doing actually before the weather got so bad outside. Now look at this. Now we start with Paul's Pauli's exclusion. Look at this exclusion principle. What is this thing all about? He said no two electrons in an atom, no two electrons in an atom have the identical set of four quantum number. Now we have mentioned something, quantum number from this Pauli's exclusion principle to quantum number. Now let me just short form it. When we talk about quantum number, there are simply set of numbers used to assign electron across the various orbitals. Yeah, set of number that we use to assign electron across the various orbitals. Last time, for those of you that have been consistent, last time while we were in this media space, we started from the very elementary part, which is the part of your JAMB Chemistry, or first part of what you need to know before sitting for this exam. We started with matter. I told you matter is anything that has mass and occupies space. Matter is anything that has mass and occupies space. We say so many things about matter, pure substance, impure substance. I'll give you what we call the percentage test for purification or purity of substances. Now, there are so many things for us to talk about, but I just have to do everything possible to, make sure that I give you the concise version of it. Yeah. Pauli's exclusion principle, like I said, is what? A principle that said that no two electrons in an atom have the identical set of four quantum number. Meaning, what quantum number is all about, we need to know. So, quantum number is just set of numbers used to describe electron across orbitals. Remember, from quantum number, I mentioned another ambiguous or another term that you are not fantastically used to. I mentioned orbitals. Now, for orbitals, I told you time before now that this is the region in space where there is what? High probability of locating an electron. Yeah, high probability of locating an electron. That is what an orbital is. Yeah. Before orbitals, let's talk about four quantum numbers. Four type of quantum number that we have. Four type of quantum numbers. We have what we call the principal quantum number. Principal quantum number. Now, what is the work of this principal quantum number? You need to understand that principal quantum number, you would have seen the other side. Okay, now principal quantum number determines what we call the size and energy levels of an orbital. Please, if you are together with me in this media space, do well to keep sending reaction to the video. Yeah, keep sending reaction. We are going to just little time of teaching, then we dedicate the rest of the time to solving questions. Now, principal quantum number determine what we call size and energy level. Energy levels, are you seeing it? Of an orbital. Size and energy levels of an orbital. That is the work of principal quantum number. Determine the size and energy levels of an orbital. Then when we talk about the azimuthal, as I mentioned before our network get disturbed, azimuthal quantum number, let me short form it. Don't forget the symbol for principal quantum number is N, as this one is L. Azimuthal quantum number is that quantum number that determines the shape of an orbital. I'm going to take you this as a topic of its own, but let's just discuss three basic principles of assigning electron across the various orbitals. Now, azimuthal quantum number, what is the work? It determines the orbital shape. So let's put shape. And that is why you should know there is a value for at L equal to 0. It stands for what we call S orbital. S orbital. Whenever the value of azimuthal is 0, it means S orbital. And the question is, what is the shape of S orbital? S orbital is spherical in shape. Spherical in shape. Are you seeing it now? Spherical in shape. Don't forget, I said the work of azimuthal quantum number is to determine what we call the shape of an orbital. Yeah, it determines the shape of an orbital. That is the work of azimuthal quantum number. So when the value of L is 0, it's standing for what? S orbital. And the shape of S orbital is what? Spherical in shape. Now when we talk about at value of L equal to 1, it stands for P orbital. P orbital. Yeah, P orbital. And the shape of P orbital is what? Dumbbell. Dumbbell in shape. It is dumbbell in shape. And of course, at L equal to what? 2, we refer, we talk about what? D orbital. It's S orbital that it represents. And that have their definite geometries. Like the geometric shape of S is what? Spherical in shape, as P is dumbbell. Then D orbital, double dumbbell. And you know, for F orbital, you know, when okay, S block element of the periodic table, you know that your group 1 and group 2, which is alkaline metal and the alkaline earth metals. So while we will talk about the P block element, these are the different, we call it blocks, SPDF block. So P block elements, yes, you know, from group 3 and above, while D block elements are your first transition element, as the F block are the inner transition element. So this is F block, and it is compressed or complicated in shape. Compressed or complicated, compressed or complicated in shape. Yeah, that is it. You must know their respective shape, the shape of these various orbitals. They are very important. Yeah, very, very necessary as you approach the exam hall. Know the shape of S, know the shape of P, know the shape of D, and know their respective shape. That is just it. Now, when we talk about magnetic quantum number designated as ML, magnetic quantum number, that is ML. Number one thing I want you to understand, there is no time, is that your magnetic quantum number value depends on the value of the word azimuthal. It ranges from minus L to plus L. That is why, for instance, if the azimuthal is 0, this implies that your ML will also be 0, because there is nothing like minus 0 to 0. But if the azimuthal is 1, this implies that it will now ranges from, your ML will now be minus 1, 0, and plus 1. Now, permit me to say, the work of this magnetic quantum number is to determine subshells, or what we call the degeneracy in an atom. What do you mean by degeneracy? When we mention degenerate orbital, what do you mean by that? They are simply orbitals of same energy level. Subshells, yes, subshells that are degenerate, or degenerate orbital means subshells. Okay, now that aside, and when L is 2, now you can see that your ML will range from minus 2, minus 1, 0, 1, and 2. Now with this, now if they ask you how many subshell does S orbital, because you know at the value of L equal to, at the value of L equal to 0, are you seeing it? We are talking about S orbital. And since S orbital have only just one column, that means it have only one subshell. But the value of L equal to, look at this, 1, we have minus 1, first subshell, 0, and plus 1. It means that P orbital, because this P orbital, have 3 interior compartments, that is 3 subshells. Now we have it as Px, Py, and Pz. While at the value of L equal to 2, we have minus 2, minus 1, 0, 1, and 2. 5 different subshells. 5, and that is d orbital. And of course, at your L equal to 3, we have the ml to be minus 3, minus 2, minus 1, 0, 1, 2, and 3. This is 7 interior compartments, and that is f orbital. And now, we are just deliberating on what we call Pauli's exclusion principle, that state that no 2 electrons in an atom have the identical set of 4 quantum numbers. From Pauli's exclusion principle to mentioning quantum number, which are a set of numbers used to describe electron across the various orbitals. Are you seeing it now? Now, we have mentioned principal quantum number that determines size and energy levels of an orbital. We have mentioned azimuthal quantum number that it determines what we call shape of an orbital. Then we have mentioned also magnetic quantum number. What do we say about that? That it determines the subshells, and of course spin, the last quantum number. Remember, it is this spin quantum number that brought variation or violation to Pauli's exclusion principle. This is what spin quantum number. The symbol is ms, spin quantum number. What does this spin say? It says an electron must not be oriented towards same direction. Yeah, that. Look at this. I want you to know that the 2 possible values of spin is plus or minus 1 over 2. It simply shows that if one electron is facing up, the other one should be facing down, in order to avoid steric repulsion. Yeah, 2 electrons must not be, look at this, you can have this, either this, okay, or this, but not this way. You cannot spin this way. An electron must not be spin this way, or this one is not correct. Are you seeing it? Or you are facing it down, either up, or down, down. That is not correct spin. So take note of that. This is the best spin, or you use it as this, using half this thing. So that is how to spin electron. So we're done with that aspect. So let's go to the next orbital. Let's we have deliberated on that. Let's go to the next principle. And what is the next principle? That is what we called, the next one is what we called Hund's rule of maximum multiplicity. Hund's rule. Hund's rule. Yeah, what do Hund's rule say? Hund's rule said an electron must first be shared singly before pairing takes place in an atom. For instance, if you look at a carbon atom, carbon have 6, and of course we have something like 1s2, 2s2, and 2p2. Are you seeing it now? See, we don't have issue with this, we don't have issue with this. Where the issue is this one, because it is not a completely filled shell. So when you draft out this, p orbital have 3 interior compartments. Look at this, in place of your px, py, and pz. Hund will say that you should allocate this electron in p 1 first, meaning you are coming, remember what we have here in carbon atom is 2p2, that is p2. Yeah, these 2 stand for energy level, while these 2 stand for electron. Understand what I said? As you have 2p2, this normal 2 stand for energy level or shell, while this one stand for electron. Know the difference. So know the difference, very important. All these are the minor matters that is making you lose interest in chemistry, but the more you pay attention to me, the more you got enlightened, and the more you do better. So that is why you should keep to the rules and regulation of this. Okay, now look at this, everybody. I want you to understand this 2p2. How do you go? This is the electron that we are to share. You are not to come here and drop the two electrons up and down. You have failed. You have violated Hund's rule. Because you say, just like we are all, some of us are single, some are married. You see, before getting or saying yes I do to your second party or your missing rib, you see, you must first of all enjoy your what single life. That is the same thing this principle is trying to talk about. Share electron singly before pairing take place. So that is why picking these two, I will give this one 1. There's no need of coming to say drop the other one. No, and you give this one 1. That is it. Please, whenever you are in this media space with me, do well to send the reaction to the video. Yeah, send the reaction. Just keep reacting. Send the reaction so that others can easily discover us. Send the reaction. Send the reaction. That is a way of encouraging me to do more. Send reaction. Let it be active enough. Let me know that I'm not having ghost audience. Do it to send reaction. Send reaction. Send reaction. Send reaction. Okay. All right. So we'll soon be done with this. So this is how you share this electron across this particular 2p2. This is how you share it. This is how you share it. Very easy. Don't forget that. Very, very easy. So we are going to the next rule. We call this rule Aufbau. Aufbau principle. I want to draft something. Aufbau principle. Now, what does it say? He said that an electron must first occupy the lower energy level before that of the higher energy level. That's what Aufbau said. An electron must first occupy the lower energy level before the higher energy level. So that is Aufbau. Now, we are going to have something like this. Permit me. Let's go this way. We have 1s, 2s, 3s. All these numbers at the back of the respective orbital stand for energy level. 3s, then we have 4s, we have 5s, we have 6s, and then we have 7s. So we now have 2p. P stands from energy level 2, 3p, 4p, 5p, 6p, and 7p. Pay attention. Then we go again. We have D stand from 3 energy level 3, 3d, 4d, 5d, 6d, and then 7d. Okay, we're going somewhere. Then what again? We have 5f, we have 6f, and 7f. Now I've outlined the relative distance. Now look at what you have to do here. I'm going to join. What do Aufbau principle say? Say an electron must first occupy the lower energy level before that of the higher energy level. This is it. You will first of all fill in 1s. Are you seeing it? When you fill 1s, then you can now fill, of course, from the direction of Mahalu. What do you understand? You fill 2p before 2. Yes. You feel to sorry. There's an oversight. Yeah, pay attention. That is why. Now look at this. After filling 1s, you fill 2s. After filling 2s, you fill, this is, sorry, yeah, that is it. You fill this way. And we put this big. This is 2p. 2p. I'm going to give you that. You fill 2p before what? 3s. After that, you fill 3p before 4s. In that order, this is how it's supposed to be. This is it. Sorry, because of the way I position my book. That is how it's supposed to be. That is how it's supposed to be. So in conclusion, it means that according to Aufbau principle, that you will fill one s orbital, then you get to 2s, then you get to, from 2s you get to 2p, from that you get to 3s, from that 3s you get to 3p, from 3p you get to 4s. These are where you can easily, this alone contain the first 20 elements. And of course, from this 4s, you get to what? 3d. You see a question like this. Why is 4s orbital few before 3d orbital? Because this seems to be higher in energy level than this. But of course, you know, there's a lot of complexities in 3d orbitals, partially fused state and the rest of them. But you see, 4s come first before this. It is according to Aufbau principle. Aufbau, yes. So after 3D, you can now go to something like 4P, then dot, 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 according to these charts. You can see it. Let me explain. 1S to 2S to 3, because the arrow is pointing this way. The arrow is pointing this way, and that is why you need to understand it. After this, to this, to this, to this, this, that is, you turn and go this way, turn and turn again, according to the arrow direction. That is how to fill. It's very easy. So you should take note of that. Very, very easy. Very, very easy to fill. So that is it. Now, you see, for instance, you know, your first 20 element, hydrogen, being number 1. You just put it as 1s1. You stop at that. Then when you go to number 2, which is what? Number 2, which is helium, you become 1s2. And this is a noble gas. You can helionize it. You can also have noble gas representation as this. When you go to number 3, which is lithium, that will be 1s2. After filling 1s2s, 2s1. 2 plus 1 is 3. That gives you the atomic number. And you can also helionize it, because 1s2 stands for helium. Until you meet the next noble gas, this noble gas notation, you can have 2s1. Do you know what this configuration type easily shows you? It can easily help you to get what we call the valence electron configuration, because outside the noble gas shell, whatever that remain at this other side give you what we call the valence electron configuration of the given element. JAMB have asked before for chlorine, and of course, you know, chlorine, we are not going to be mentioning helium. You are going to encounter after helium, the next noble gas is neon. Then after chlorine, the next noble gas is argon. In that order, you go to krypton and the rest of them. So that is it. So what we are saying in essence, if you go to number 4 now, number 4 is beryllium. That will be 1s2, 2s2. Now this shows you that you see that with this now I can easily tell you, because of this 2s1 here give me a lot of information about lithium. It shows that lithium is group 1, because whatever electron, for all s block elements, the highest number of electrons that s can contain is 2, and this one shows it is group 1 element. If it is 2, group 2. But this number at the back of s here shows the energy level, which is corresponding to the period or the shell. So just the information that we got there, group 1 period 2. Now if you come to this, you have this as, you can helionize it. Look at this, and you put 2s2 that remain. Now it shows that beryllium is group 2, of course s block element, and period 2, group 2 period 2. Now let's go to number 5, which is boron. You can see 1s2, 2s2, 2p1. So with that, you see you have helium, 2s2, 2p1. Now of course, this number, since they are same, it shows that what beryllium is, because this is the valence electron configuration of beryllium. This 2s2, 2p1 is what we call the valence electron. That is the essence of this noble gas configuration. The valence electron configuration, yeah, of boron, rather, of boron. Now, what happened here? What do you need to understand? This 2 that is the same shows you what we call the what? The period, the energy level. Why? If you want to get the group, since this is not an S block, it's a P block element, whatever electron that is attached to P, add it to the penultimate S. So it is going to be 1 plus 2. 1 plus 2 is 3. That shows that boron is, instead of using, because at times, now let me show you something. You already know boron is number 5. You just say, oh, 5. That make it 2, 3. How many share? 1, 2, period 2. What is valence electron? 3. That means it is what? Group 3 element. Quite easy. No issue. But you can also use this pattern. You don't know where you'll be meeting this, or the kind of question that you are going to be seeing, that will give you configuration at time and ask you to show their valency or their combining power, that X is this configuration, Y is this configuration. Now, they say combine, that is a chemical combination too, using valency. You know all this. Now, we are going to do that anyway. Now, look at this. So, you can easily say 1 plus 2, 3, if it is P block that end it. But if it is S, like what we have here, this is group 1, this is group 2. Because S block elements are just group 1 and group 2 elements. The alkaline earth metals, which is group 2, and the alkaline metal, which is group 1. That is your S block element. Now, if you go to number 6, which is carbon, number 6, which is your carbon, what do you need to know there? You become 1s2, 2s2, and 2p2. Now, let me shock you. This is going to be helium. Are you seeing it? Because that is the noble gas that we have encountered so far. It becomes 2s2 and 2p2. Now, the valence electron configuration of carbon is 2s2, 2p2. This number shows their period. Oh, what is it? Once you see the highest number, because in this 1, 2 is greater than 1, so automatically carbon is a period 2 element. Even if you do 2, 4 for this 6, it shows 2 shells. So it's a period 2 element. Now, since it is a P block element, whatever electron at P, add it to the penultimate S. 2 plus 2 is 4. With that, carbon is group is what? Group 4. Period is period 2. That is just how to know this. It's very, very easy. That is why I'm urging you, whenever you are in this meeting, do well to, sub here. Connecting. Okay. So the other to discover our presence here. Now look at this. If you go to, I want to show you what you are going to encounter next. Look at number 7, which you know is what? Nitrogen. And nitrogen, I told you this is the order of, after filling 1s, go to 2s. After that, 2p. After that, 3s. But don't forget, you see this, the highest electron that S can receive is 2. P can receive, let me put it this way, 6. Then D can receive just 10, as F can receive maximum of 14. Are you seeing it? This is the highest number of electron that they can receive. Highest number or maximum number of electron they can receive. Don't forget that. The maximum number of electron they can receive. Take note of this one. Yeah, the live session was initially going fine using my white marker board, but the weather and everything got disturbing, so I just want to see past the information across. So for nitrogen now, you are going to have 1s2, 2s2, 2p3, as easy as ABCD. And with that, you can just heliumize. Then, of course, you put 2s2, 2p3. So this 2s2, this becomes the valence electron of nitrogen. If you go to number 8, I will just stop at the next noble gas. You go to number 8. Number 8 is our oxygen. That will become 1s2, 2s2, 2p4. That means 2 plus 2 plus 4, that is 8. Now with that, that will give you helium, helium, 2s2, 2p4. Remember, this 1s2 stands for helium, meaning it will encounter the nearest number. Okay, number 9, look at number 9. That is to say, period 2 element, maybe, okay, you see from, I think period 2 started from lithium down to neon. Look at this. Look at this. Number 9 is what? Fluorine. And that will be 1s2, 2s2, and 2p5. And that will give you helium. Helium, 2s2, 2p5. While number 10 is your what? Neon. Look at this. You have 1s2, 2s2, 2p6. So mean the second shell of p orbital have been completely filled. So with that, you are not going to add helium again, because you have encountered the next noble gas. You neonize. Look at this, you neonize. Of course, number 11 now being sodium will be sodium. Automatically become easy. 1s2, 2s2, 2p6. After filling 2p, what is the next orbital? You go to 3s. So meaning we are bringing 2 plus 2 plus 6 is 10, remaining 1, so 3s1. This, since you are an s block, it means that you are period 3 but group 1. Now look at this. Let's do something differently. You see here, sodium can also be represented thus. From 1s2, 2s2, 2p6, it represents neon. So you neonize, can be neon, then 3s1. If tomorrow they ask you the valence electron configuration of sodium, this is what you have to give them. This is what you have to give them. Just like JAMB asks for chlorine. Chlorine now. Chlorine, you are going to, after chlorine, so you are going to put neon. And you have 3s2, 3p5, because 5 pro, this is, so this is noble gas representation of chlorine, meaning the valence electron of chlorine is your 3s2, 3p5. And there, so when they ask you simple question, your ability to identify question being simple is your preparedness. Yeah, I've really exhausted. I just wanted to explain 3 basic principles of assigning electron across the various orbitals. Of course, I mentioned Pauli's exclusion principle, which state that no 2 electrons in an atom have the identical set of 4 quantum numbers. Then we move it down to what we call Hund's rule of maximum multiplicity. What does it state? It said that an electron must first be shared singly before pairing takes place in an atom. Then not just that, we also talk about Aufbau principle. Aufbau is what it does to this. What does it say? It said an electron must first occupy the lower energy level before that of the higher energy level. So that is it. So I pray we have done with the basic principle that you need to know. So maybe subsequently, I'm going to use my board and dish out questions upon questions with you guys. Our time is already fast spent, but don't forget the concept of quantum number. I told you quantum numbers are numbers used in arrangement of what? They are numbers used in arrangement of electrons in shells of atoms. We have what we call principal quantum number, azimuthal or subsidiary or angular momentum quantum number. We also have what we call magnetic quantum number and spin quantum number. I told you that magnetic, starting from principal quantum number, that it determines what we call the size and energy levels of an orbital. Of course, when we talk about azimuthal, it determines shape. It determines subshells, and we talk about spin, we talk about orientation of electron, that electron must not be facing same direction at the same time. If one is pointing up, the other one should be pointing down. And as a student preparing for this exam, don't forget that the two possible values of spin remains plus or minus 1 over 2. Okay, I think with this, we just take a pause. See you in my next live session. Thanks for joining today. Have a wonderful day. Mm. Mm. This weather really disturbed my this.